Hello everyone, hope you are all doing fine. Welcome to the first video on electrostatics. Electrostatics basically is the study of charges which are at rest. So we are going to study the charges that are at rest. In this video, we are going to learn about most fundamental concept of electromagnetism, that is charge. Charge is knowingly, unknowingly involved in our day-to-day life, from lightning to charging a mobile. So yes, my name is Vijay Krishna and you're watching UpPhys channel. Let's get started. First, let us understand the definition of charge. Charge is a fundamental property of bodies due to which the objects either attract or repel through electromagnetic interaction, or we can simply say that electric force. Okay, so when charges are brought near to each other, they attract force on themselves. Okay, now charge is usually measured in terms of coulomb. That means the unit of charge is coulomb. Unit of charge is coulomb. Coulomb is usually represented with capital C, as we all know. Though it is a fundamental property of the bodies, it is not a fundamental quantity. So we need to express this charge in terms of fundamental quantities in order to express the dimensional formula of the charge. Now coming to the dimensional formula of charge. We need to express this charge in terms of fundamental quantities. As we all know, the definition of current is charge flowing per unit time, rate of flow of charge per time. So if I rearrange this equation, Q is equal to I into T. As we all know, this I is a fundamental quantity and time is also a fundamental quantity according to SI system of units. So Q dimensional formula would be, the dimensional representation of I is A and the dimensional representation of time is T. So the dimensional formula of charge is AT. Okay, and as we all know, this charge is a scalar quantity. It is independent of the direction in which we are going to measure the charge. Okay, so it is independent of the direction, rather we consider only the values, whether it may be positive or negative. Now let's move on to the next point, that is fundamental, I mean the smallest unit of charge. Smallest unit of charge. Smallest unit of charge is charge of an electron or proton, as you can say, because there are two types of charges. Okay, universally accepted that the smallest unit of charge is charge of either electron or proton, and charge of electron is 1.6 times 10 to the minus 19 coulombs minus, and proton charge is 1.6 times 10 to the minus 19 coulombs again, but this time it is plus. So electron is negatively charged and proton is positively charged. Now coming to the next set of points. Okay, so smallest unit of charge is plus or minus E, and there are two types of charges. There are two types of charges, positive and negative. Okay, when you look at the atom, nucleus will be at the center and all the electrons will be revolving, or actually revolving around the nucleus, and nucleus has protons and neutrons. Protons and neutrons, and the electrons are revolving around the nucleus. In electrostatics, neutron has no significance because it has no charge, it is neutrally charged, but proton and electron has proper significance. So when it comes to positive charge, if I want to make an object positively charged, then I will remove the electrons. Okay, and if I want to make this object or any object negatively charged, then I have to add the electrons. Why am I saying adding or removal of electrons instead of saying in order to make an object positively charged? Why can't I give the protons instead? Okay, this is because protons usually lie in the most stable part of an atom, which is called nucleus, and in order to remove the proton, it requires so much amount of energy, maybe nuclear reactions. So, and if I remove one electron, let's say I've taken sodium, okay, let's say I've removed its atomic number is 11. This atomic number is defined by using proton number, not based on the electron number, because electrons can be removed or added. So Na has 11 electrons and 11 protons, and this atomic number 11 is defined based on the number of protons. Okay, let's say I have removed one proton. Proton removed. If one proton is removed, how many number of protons are there? There are only 10 protons. If there are 10 protons, then the atomic number of the given substance or the object changes. If the atomic number changes, then the object or the atom or the system that is given to us will be configured into some other object or element or atom. So if I would have taken one proton from the atom, from the nucleus of course, then only 10 number of protons remains. That means this sodium will turns into neon. So we don't want the element to change, we don't want the object to change, we want the object to get charged. Okay, so instead of changing the object, we are just charging the objects. Okay, in order to do so, instead of adding or removing the protons, I am just simply adding the electrons to make the object negatively charged, and I'm just removing the electrons to make the object positively charged. Let's say if I would have taken sodium again, let's say one electron removed out, one electron is removed, then what happens? This sodium will becomes Na plus. The element or the object or the atom will remain same as it is. Okay, the configuration or the properties will not change, rather it will acquire positive charge. Similarly, if you take chlorine, it has 17 number of electrons and protons. Let's say I have taken out one electron, then what happens? Then it will I have added one electron. Let's say I have added one electron added. If one electron is added, then Cl would become Cl minus. That means it becomes negatively charged. So the conclusion is, in order to make an object positively charged, I have to remove the electrons. In order to make an object negatively charged, I have to add the electrons. So there is a misconception. You may come across some sort of misconception like in order to make an object positively charged, we have to add the protons. No, that is wrong. So in order to make an object positively charged, we have to remove the electrons. Okay, we have to make the protons dominant. That is how we can make any object turns into positively charged. Okay, so smallest unit of charge, and I forgot to tell you the mass of electron is 9.1 times 10 to the minus 31 kg, and mass of proton is 1.67 times 10 to the minus 27 kg. I am giving these values because sometimes you may come across a situation where the question is asked but this data may not be given in the question, may not be mentioned in the question. In such cases you need to remember these numbers, because these are the fundamental numbers you may see in chemistry, mathematics, so I mean chemistry, physics. So these are the fundamental numbers which we need to remember. Okay, so and let's move on to the let's learn the okay now let's learn the properties of charge. So fundamentally the charge, any charge will have some properties, will exhibit some sort of properties. So let's learn those properties. Okay, first one is charges are interactive. Charges are interactive. This means when we place the charges near to one another, which means relatively close to each other, then each of these charges will exert some sort of electromagnetic interaction on the other charge. Okay, or simply we can say they exert force, electric force on each other. Okay, now if I have taken similar type of charges, positive and positive, positive and positive, positive and positive, then there exists repulsion, or as you can take negative, there exists repulsion again. So like charges repel each other. When it comes to unlike charges, let's take a positive charge and a negative charge separated by a certain distance, considerably close to each other, then they exert attraction. They attract each other. So I can say unlike charges attract each other. So this kind of interaction will happen when charges are brought relatively close to each other. Okay, now we will learn the interaction between the charges, that is electric force, in the next video in Coulomb's law in electrostatics in detail, along with the examples and properties and more examples, and the previously asked questions in the IIT, JEE, NEET exams. So those points will be discussed in the next video, but in this video these are the points that we consider the properties of charge. Okay, so charges interact each other through electric force. Like charges repel each other, unlike charges attract each other. Now coming to the next property, quantization of charge. According to quantization of charge, charge of any body is equal to integer multiple of smallest unit of charge. Smallest unit of charge that is universally approved or accepted is charge of an electron. or a proton, as we can say, because those two have the same charge except they have opposite polarity. So total charge of a body is equal to integer multiple times of smallest unit of charge. Okay, of course, even though it is universally accepted that the charge of electron or proton is the smallest unit of charge, but still we still have even smaller charges. We call them as quarks, which comes out to be 1/3 of electron, 2/5 of positively charged positron or electron. So these kind of charges also exist, but so far and universally the fundamental or the smallest unit of charge has been accepted, that is charge of electron, which is total charge of any body is equal to integer multiple of smallest unit of charge. Okay, why this electron or proton is considered as smallest unit of charge? Because if you consider any atom, like we have discussed in the earlier slide, if you consider any atom, all the protons lie in the nucleus, all the electrons will be revolving around the nucleus, and all the electrons will have the same charge, all the protons also have the same charge. Electrons and protons also have the same magnitude of charge, but of opposite polarity. Electron will have negative charge and proton will have positive charge. So I cannot identify, or I cannot create half of an electron or 1/3 of an electron, 2/5 of an electron, because that is not possible. Okay, so as I can gain only, I can grab only 1 electron, 2 electron, 5 electron, 10 electrons. So I can give 2 electrons to a body, or I can take 5 electrons from a body. So total charge of a body can be expressed as integer multiple of charge of an electron, or smallest unit of charge. So let's check. Okay, let me give you one more example. If I would have taken carbon, let's say, if I would have taken carbon, if I have taken carbon, okay, if I have taken carbon, there will be 6 electrons and 6 protons, right? So 6 electrons and 6 protons. Okay, I cannot find 2.5 electrons. No, this is not possible, right? And similarly, if you take sodium, in that atom we will have 11 electrons and 11 proton. I won't be able to find 10.5 electrons or protons. So electrons are always available in terms in integers. Okay, so what I'm trying to explain you is, so electrons are always available in integers in any body. That is the reason quantization of charge explains that total charge given to or taken from any body is equal to integer multiple of smallest unit of charge. This charge can either be positive, or negative. So that's the reason total charge of a body can be represented as plus or minus integer multiple of smallest unit of charge. I hope you understand the point behind this quantization of charge, or the logic behind this quantization of charge. It is a very important property of the charge. Okay, now let's check how many electrons are to be removed or added to acquire 1 coulomb of charge. Okay, so let's say a body is given with 1 coulomb of charge. Let's say it is positively charged. Okay, so I have identified the body has 1 coulomb of charge, positive charge. If a body has positive charge, then the electrons are being removed, right? So now let's find how many electrons are being removed to have this 1 coulomb of charge. So I know Q is equal to NE, okay, and I know Q is equal to 1 coulomb, Q is equal to 1 coulomb, okay, is equal to n, I don't know, that I am going to find, and E means charge of either electron or proton. I am writing it as 1.6 times 10 to the minus 19 coulombs. Now let's find n value, which is 1 by 1.6. This 10 to the power minus 19 in the denominator will goes to the numerator, which will become 10 to the power 19. Now if I calculate this value, 6.6 something, 6.625, let's say 6.625 into 10 to the power 18. So in order to get 1 coulomb of charge, I require 10 to the power 18 number of electrons, which is not a small number. So that's the reason we often represent the charge of the objects or the bodies in terms of millicoulombs or microcoulombs, sometimes nanocoulombs, sometimes even femtocoulombs, picocoulombs. Okay, so we represent the charges in such manner in terms of milli, micro, nano, and pico, femto terms we use to represent the charge, because 1 coulomb is a very large value. 1 coulomb is a very large value. I hope you understand this quantization of charge. Now let's move on to the third property of the charge, that is conservation of charge. Conservation of charge. Conservation, like energy and mass, like energy and also the mass, the charge also conserves for an isolated system. How we define or state the conservation of energy? It's something goes like energy cannot be created or destroyed. It can be transferred from one form to another form or one body to another body, as you can say. But however, the total energy of an isolated system remains constant. Okay. Likewise, we also define the conservation of charge, like it goes like charge cannot be created, cannot be destroyed, because charge no one has created the charge, it already pre-exists in the atoms. Okay, the charge, as you can say, electron is being invented, not created. So electron is already there in the atom. So J.J. Thomson has identified or invented there is an electron in the atom. It's not like he has created. I cannot say I have created 10 electrons today. Okay, or I can say I have destroyed 5 electrons today. I cannot say that, because charges cannot be created or destroyed, but they can be transferred from one body to another body. That we are going to learn. So they can be transferred from one body to another body. That is the reason we are getting electric shocks, because charge gets passed through our body when we put our fingers in the plug points, sockets. So charge gets transferred from one place to another place, or one body to another body, or one point to another point. But however, charges cannot be created, cannot be destroyed, but can be transferred from one body to another body. However, total charge of an isolated system remains constant. I am going to write the statement here. First point is charge cannot be created or destroyed cannot be created or destroyed. It transfers from one body to another body. Total charge of an isolated system remains constant. Anyways, I'm going to explain how it works. Okay, I'm taking off all these things. One moment. Okay. Now, okay, let me give you one example how charge is conserved. For example, let's take an isolated chamber. I'm going to take the bigger one. Okay, sorry. Okay, I've taken an isolated chamber in which I have identified, let's say, 5 particles. Okay, this is one thing, and these are the 5 particles that I have identified. And I have also measured the charges on each particle, like 6 coulombs, 6 coulombs, 5 coulombs, 2.3 coulombs, let's say, and this is minus 2 coulombs, minus 1.5 coulombs, 1.6 coulombs, let's say. Okay, so these are the particles with charges that I have already represented on the diagram. Now let's take this chamber or a container, and I have shaken it for some time. Then I have kept it like this. Now I picked up the same particles, they are somewhere around. Okay, now the charges have become, let's say this is 1.8 coulombs, and this is minus 9 coulombs, and this is minus 9 coulombs, and this is 2.3 coulombs, 6 coulombs, and this is Q, and you are asked to find this Q value. Okay, but however this is an isolated system. Charges neither escaped from the system nor added into the system. So whatever the charge which is initially there, the same amount of charge should also be there at the end, right, after some activity. So according to conservation of charge, total charge initial is equal to total charge final. If you take the initial charge, as I've already mentioned, charge is a scalar quantity. You can add them algebraically. You don't need to consider their direction. So I'm going to write them directly. 6 coulomb of charge plus 5 coulomb of charge minus 2 coulombs of charge plus 2.3 coulombs minus 1.6 coulombs is equal to whatever the charges are here, you can write. So 1.8 minus 9 plus 2.3 and 6 plus Q there. Okay, we need to find this Q value, right? Let's find it out. Now what is this total value? 6 plus 5, 11, 11 minus 2, 9, 9 plus 2.3 is 11.3, 11.3 minus 1.6, 11.3 minus 0.6, 10.7 and 9.7. So this is 9.7 is equal to what is here, 1.8, 2.3, how much, 2.3, 3.1, 4.1, 4.1 plus 6, 10.1, 10.1 minus 9, which is 1.1 plus Q. So I need to find this value, this Q should be equal to 9.7 coulombs minus 1.1, which is equal to 8.6 coulombs. So this is the charge on the unknown charged particle Q. So this is how conservation of charge works. I'm going to give you one more example to give you more clarity on this conservation of charge property of the charge. So yeah, I'm gonna take this one out. Sorry. Remove. Okay. Yes. Okay. So yeah. Let's take one more example. To make you understand it better, I'm going to take two identical spheres, metal spheres. Okay. So let's take this one as metal sphere 1 and this as metal sphere 2, which are identical metal spheres. Identical metal spheres. Identical. Why I have taken identical metal spheres, that you will be able to understand in a minute. So let's just say say these two charges are initially neutrally charged. There is no charge. Okay, no net charge. What do you mean by neutrally charged? Actually, there exist charges. Protons also will be there in the metal, or electrons will also be there. But the only thing is electrons and protons bound together and becomes neutral. Okay, so the term neutral means electrons are there, protons also there, right? But they bound together so that the objects or the metal spheres here are neutral, or become neutral. Okay, now how I have provided certain amount of charge to this object. Let's say I have given 10 coulombs of charge. How much? 10 coulombs of charge. I have given 10 coulombs of charge. I have given 10 coulombs of charge, and the charge initially on this object is 0. Is 0 because all the electrons and protons are bound together and becomes neutral. Now what I am going to do is I am going to put them in contact with each other. So this is the sphere 1 and this is sphere 2. I put them in contact for some time. In contact for some time. Then what happens? It has 10 coulombs of charge and it has 0 coulombs of charge. Now what happens? Charge flows. From which body to which body? From higher charged body to lower charged body. Exactly, this is not the statement which is correct. Charge always flows from higher potential body to lower potential body. This is the right way to say that. Okay, it's not the right way to say like charge is flowing from higher charge body to lower charge body. No. Okay, charge always flows from higher potential body to lower potential body. Like wind blows from higher pressure to lower pressure, or temperature flows from, or heat flows from higher temperature to lower temperature. Similarly, charge flows from higher potential body to lower potential body. But as far as for now we have no much clarity on the potentials. That's the reason I have taken two identical spheres, because if two spheres are of identical, that means they have same shape, same size, same nature of the bodies. So that's the reason I have considered these two bodies are identical. If the bodies are identical, then when their potentials are same, then the charges also should be same. Okay, so you will be able to understand this potential concept in the later sessions. Okay, that I am going to explain in a detailed manner. But for now, consider these two objects as identical objects, and the charge is flowing from higher charge body to lower charge body. In general, higher potential body to lower potential body, as we have considered identical bodies, so higher charged body to lower charged body. Now charge flowing, to what extent the charge flows, to what time the charge flows. That means charge is flowing from higher potential to lower potential, here the higher charge body to lower charge body, till the equilibrium is obtained. What do you mean by the equilibrium? Equilibrium in the sense potentials same, charge flows till the equilibrium is obtained. What do you mean by equilibrium? The term equilibrium means potentials same. As I have considered both the objects as identical objects, so in our case, charge same. So this may not be possible every time, okay, unless the two objects are identical, same shape, same size, same material, okay. Unless these two are identical, this condition will not work, but this condition works every time, okay. So potentials are same. In our case, the charges same. That means both the objects will gain the same charge. I'm going to take this one out, okay. So potentials same. Okay. So in our case, charges same, okay. Now finally, I have separated the charge transfer is taking place. Charge is decreasing, 10 coulombs, decreasing, excuse me, and charge 0 coulombs, increasing, right? Till what extent the charge increases? Till the equilibrium is obtained. Up to equilibrium. Okay. Okay. When the equilibrium is obtained, the charges on both objects should be same. Let's say the charge on this one is Q, charge on this one is also Q, right? According to conservation of charge initial is equal to charge final, right? According to conservation of charge, as the two objects have been considered as an isolated system, okay. So what is the initial charge of the system? This is 10 coulombs and this is 0 coulombs. That means total charge is 10 coulombs only. 10 plus 0 is equal to, now what is the total charge at the final stage, which is Q plus Q. Now what would be the charge on each sphere, which is 5 coulombs, So charge has been equally distributed to the objects because we have considered two identical objects. So this may not be possible every time, okay. Now let's say I've taken another object this time. Now the objects are, this is 5 coulombs now, and this is also 5 coulombs. I've taken another neutral object, 0 coulombs. Now I put these two objects in contact, these two objects in contact, 0 coulombs. Now charge flows from high charge body to low charge body, higher potential to lower potential. In our case, high charge body to low charge body. Then what happens? Then again equilibrium is obtained after some time. That means after the equilibrium is obtained, let's say I have separated the two objects. Now these two bodies will have the same charge, which would be equal to 2.5 coulombs and again 2.5 coulombs, sorry 2.5 coulombs, 2.5 coulombs. So this is how conservation of charge works, which is again another most important property of the charge. Okay, now let's move on to next property of the charge. Okay, let's move on to next property of the charge. I'm going to take the entire screen off. Clear? Okay, now fourth one, invariance of charge. Invariance of charge. What do you mean by invariance? Invariance means charge does not change. So there are 2 points which I am going to tell you right away. First thing is, charge does not changes with medium. If you measure the charge, let's say you have measured the charge of an electron, which is minus 1.6 times 10 to the minus 19 coulombs, and this charge has been taken into some other space or water or oil or any medium, the charge of the electron will remain same. It is independent of the medium. Charge does not change with medium. This is one important point. Okay, so charge does not changes with medium. Even if you place this charge anywhere in this space or air or water or any kind of alcohol or any kind of medium, the charge will not change. Now coming to the second most important point, that is, charge does not change with its motion. Why I am mentioning this property, because when mass is moving in the medium, let's say mass is moving with a speed which is even close to the speed of light, then the mass of the particle changes significantly according to Einstein's relativity. So Einstein has defined the relativistic mass formula, which is m is equal to m naught upon root over 1 minus v square by c square. 1 minus v square by c square. Okay, so here m is the mass of particle, moving at speed v, where m naught is the mass of particle at rest. We can simply say this m naught as rest mass of the particle, and v is the speed, as we all know. C is speed of light. We all know this, speed of light. If any particle which is moving in the medium or anywhere with a speed which is close to the speed of light, which with greater speed, then the mass of the particle changes significantly. Let me give you an example. Let's take one value to understand it better. Let's say a particle moving with a speed which is close to the speed of light, which is comparable to the speed of light. V is equal to 0.5 c. 0.5 c, which is near to the speed of light. So mass m is equal to m naught by 1 minus v square. V square means 0.5 c whole square. That means 0.5 whole square into c square, which is 0.25 c square by, again we have c square, okay, and we have the under root also. Okay, now if I simplify this equation, m naught by the c square will get cancelled, and 1 minus 0.25 would become 0.75. This 0.75 can be expressed in fractions like 0.35, 3 upon 4 under root. 3 upon 4 under root. Okay, if I simplify this equation, this root 4 can be 2, this 2 can be taken to the numerator, 2 m naught upon root 3 is 1.732. So this 2 by 1.732 would give you approximately 1.13 or something m naught, 1.13 m naught. When the particle is at rest, it was really at rest, when the particle was at rest, its mass was m naught. When the particle is moving with speed which is comparable to or close to the speed of light, which we have taken 0.5 times speed of light, in that case the mass of the particle has increased by 13%. 13% it has increased. So it is considerable, right? The increase in the mass is considerable. So when the mass moves in the medium, the amount of mass increases. It's not acceptable for smaller speeds. If at all any particle moves with a speed which is close to the speed of light, then only it can be considered. It's a relativistic term. So charges are very small, right? Charge of the electron is 1.6 into 10 to the power minus 9, where its mass is 9.1 into 10 to the power minus 31, which is even lighter. So lighter particle can travel with speeds which may be equal to speed of light. Okay, so even though the charge moves with speeds which is close to speed of light or even equal to speed of light, even more, then also the charge does not change with its motion. Am I making myself clear? Am I making sense? Okay. So charge does not change with its motion. These are the 4 important properties of the charge we need to understand before we get into the applications, right? The first property is charges are interactive, like charges repel each other, unlike charges attract each other. Second property of charge is quantization of charge. Every body or any body, charge of any body is equal to integer multiples of smallest unit of charge, which is q is equal to ne. And the third property is conservation of charge. Charge we cannot create, charge we cannot destroy, but charge can be transferred from one body to another body. Total charge of an isolated system is constant. Right? Now coming to the fourth property, that is invariance of charge. Invariance of charge includes 2 points. One is charge does not changes with the medium, and the second one is charge does not changes with its motion, even if it moves with speed of light or even more than the speed of light. Okay, so hope these are the points which are clear to you. Okay, right, now let's move on to the next part of the discussion, which is electrification. Okay, electrification. Okay, let us understand what is electrification. Electrification is the process of imparting or removing electric charges to an object. The process of giving the charge or giving the charge, positive charge or negative charge. Giving the charge to an object. Giving the charge to an object is called electrification. There are different methods of electrification. Let's discuss some basic methods of electrification, among which the first stands out is electrification by friction, which is the easiest method, because every one of us has learned this electrification by friction. When we rub the bodies together, then both the objects or bodies gets electrified. Where one object gains positive charges, other object gains negative charges. Two of the object gains two different polarity charges. Okay, so electrification by friction, the definitions you can see it here. When you rub two bodies, work is done, overcome to friction. Okay, heat is produced when we rub two bodies. This heat energy will be supplied to the electrons. Electrons gains energy and they will be, they will ready to come out, or they will ready to transfer due to their excess energy. So because of which this excess energy helps the charges or electrons to transfer from one body to another body, thereby the entire charge transfers. Okay, so one object acquires positive charge whereas the other object acquires negative charge. Okay, let's see some examples. Rubbing a glass rod with silk cloth. When silk cloth is rubbed with glass, or glass is rubbed with silk, then glass loses electrons. Losing or gaining the electrons depends on the electron affinity of the material, okay, object. So glass loses the electrons means it has low electron affinity, so it loses the electrons, and silk gains the electrons. Okay, so as the glass has lost the electrons, glass will become positively charged, and as the silk gains the electrons, silk would become negatively charged. Okay, after some time these two will attract each other once they gain the charges. Now coming to the next one. When you run a plastic comb, okay, we have the comb at our homes. When we run a plastic comb in our hair, dry hair especially, comb through dry hair, the comb pulls the electrons from your hair. That means hair lost the electrons. So it gains positive charge. Whereas comb pulls the electrons. Comb has accepted the electrons or gained the electrons, so it becomes negatively charged. After some time, once they gain these charges, positive and negative, when we keep them close to each other, then they try to attract, they pull each other. Okay, now so these are some of the examples, and this is the basic process that we are learning from our childhood, right? So electrification by friction. Now let's learn the next electrification method, which is very important, electrification by conduction. Okay, this we have already discussed. I may not mention the name of the conduction, the process of electrification, but the process that we have already discussed. Okay, so as I have already mentioned in the earlier slides, like I have considered two identical metal spheres. When I put them together, when I put them in contact with each other, then the charges are being transferred from one body to another body. In that case, both the bodies have acquired the same type of charge. Like if I have, let's say I have given 10 coulombs of charge to one body, 0 coulombs of charge to other body. When I put these two bodies in contact with each other, then the charge starts to flow until the equilibrium is obtained. That means potentials are same. Of course, I have taken the identical spheres, so the charges would be same. So charges would be same in the sense both the objects will have the same charge. That means 5 coulombs and 5 coulombs. The charge transfer has been taken place. Initially, one of the sphere has no charge, 0 coulombs of charge. But now, after they put in contact with each other, as the charge transfer takes place, it has taken place. So this neutrally charged object has gained the charges. This is the basic process that we call it as electrification by conduction. So As you can see here, this involves the actual flow of electrons between the two conductors in contact. We need to put the two conductors in contact. I have given the illustration also, the diagram also. Ebonite rod. Ebonite rod is a kind of rod where insulation has taken, we are holding the rod at the insulation point, and it has the ability to acquire many number of charges. So it has the charges, negative charges. When I put in contact with the sphere, which was initially neutrally charged, then the sphere will gain the electrons, negative charges, not the electrons, gain the electrons of course. So the negative charge acquires, and the basic property of the conductor is that when the charge is given to the conductor, the entire charge distributed, or we can say redistributed uniformly on the surface of the conductor, not inside. So this excess charge is distributed uniformly on the surface of the conductor. Again, these are insulators, I mean insulated and insulated stem. Okay, so this entire thing is insulated. Only these are the conductors where the charge transfer takes place. In conduction method, the object should be in contact. Object are to be put in contact, then only the charge transfer takes place. And one more key point is, in conduction method, both the objects will have the same nature of charges, unlike in the friction method. Okay, so this is what we call it as electrification by conduction. Now coming to the next method of electrification, which is induction. Okay, induction. Again, I have taken the same system like I have shown it in the earlier slide. So ebonite rod, which has the negative charge, but this time, unlike in the earlier case, this time I did not put the ebonite charged rod in contact with the metal sphere. Rather, I have placed this rod, ebonite rod, close to the metal sphere, not in contact. Exactly what happens. So this was initially, let me draw the diagram. Okay, so initially this is the metal sphere where it has no charge. All the protons and electrons are being neutralized. They bond together and neutralized. Now let's say this is positive and negative, to showcase this positive and negative. When I put this rod, which is negatively charged, let's say negatively charged, near to the conductor, not in contact, then what happens? This negative charge repels the negative charges, it pushes the negative charges, sorry. Okay, it actually pushes the negative charge. It actually pushes the negative charges away. Okay, and meanwhile this negative charge also attracts the positive charges towards it. That means in this process, in the same object, electrons and protons are being separated. This process of separation of electrons and protons, I mean positive and negative charges, is called polarization. Plus minus separation is called polarization. Okay, so in induction process, polarization occurs. That means separation of positive and negative charges occurs in the same object. Now we cannot decide which charge the object has, because it has both electrons and protons, I mean positive and negative charges. In order to make this object positive or negative, I have to follow the next step. Okay, that step is nothing but connecting one side of the object to earth. Earth has infinite potential. It can take any amount of charge, whether it may be positive or negative. So I have connected, I want to make this sphere positive. I want to make this sphere positive. So I have to remove these electrons. To remove these electrons, I have conducted the electrons, I mean negative charges side to earth. Then what happens? All these negative charges are being transferred to earth. Then what happens? Then obviously all these positive charges will be redistributed uniformly on the conducting surface. That point I have already explained in the last slide. Okay, so what exactly happened? Let me explain it again. I have taken a neutral metal sphere and an ammonite charged glass rod, and this charged glass rod kept close to the conducting sphere, I mean the metal sphere, neutrally charged metal sphere. Then this rod tries to push the similar type of charges, that means the negative charges, and it tries to attract opposite polarity charges, that means positive charges. So at this stage we cannot decide this object whether it has positive charge or negative charge. Okay, we cannot decide that. We are not able to decide that. To make it positive, what I am going to do is I am going to connecting the negative end of the sphere to the earth. As the earth has higher potential, infinite potential, it grabs any amount of charge. So obviously it gains all the charges, it grabs all the charges which is close to earth, which is connected side, which is on the connected side. So the remaining portion, the charge on the remaining portion will be redistributed uniformly on the surface of the conducting sphere or metal sphere. So this is how induction process works, and we have the formula. We will experience this formula in the capacitors concept, but anyhow I am going to mention it here. Q is equal to minus Q 1 minus 1 by K. This Q is induced. Okay, Q induced, whatever the amount that is induced in the object, this is Q induced. Okay, Q induced. Q induced is equal to, what is this minus Q? Charge. Q supplied, charge supplied, into 1 minus 1 by K. K is what? K is the dielectric constant. For different mediums it is different. For a perfect conductor, for a perfect conductor this K is equal to infinity. So if this K is infinity, if I put this infinity here, 1 by infinity is 0, then whatever the amount of charge that we supplied or we used to induce, same amount of charge will be induced on the conductor. Okay, but with opposite polarity, as I can say, this negative sign that I have used and positive sign that I have acquired. Okay, right. Okay, so that's it in this video. I hope this video is helpful to you. Whatever the explanation that I have followed through is helpful to you. If you find the video is helpful, please do like, share, subscribe, and don't forget to hit the bell icon in order to get the notification as soon as I upload the videos. So stay tuned, and don't forget to comment below. If you like the video, comment below. If you have any queries regarding this video or regarding any subtopic or topic, please comment below. Okay, see you in the next video. Thank you so much for watching.